Let's put it here. Hello, everyone. Welcome to the second day of the winter bootcamp on deep learning. Sorry, third day. I think it's third day, right? Yeah, third day. So today, the discussion is about mainly about RNNs and some stuff related to recurrent networks and see how valid they are. And then we will also, in the first part, give the whole overview on the concept, on why it is relevant, how it is made, and things like this. And the second part will be mostly focused on coding. We will code a real project with like real data, and we will train a model on it using an RNN. So this is the general idea of today. If you know RNN, like almost basically like the whole first week of the bootcamp, if you already know, it would be mostly repetitive for you, so it might be boring. But if you don't know, it would be it would be very nice to indeed start with. So as I said, the first part would focus on the underpinning of the RNN. We will first start with the recap, and then we will get through a code in the second part. My idea is to have also a bit of gap in the between two parts so that it's not very difficult for you to listen for 3 hours. I think we can have a gap on 5:15, so it would be like 1 hour the first slot, and then like maybe 10 minutes or so, and then we'll start the second part until around 6:30, 6:45, if that's fine with you. All right. So I will start. Maybe just wait. It's for 8, maybe just 2 minutes, and then if someone is coming, and then I will start. If you have any questions in the meantime, just let me know. It's in the Zoom link for the bootcamp. The Zoom link in the group. Could you find this? We just send it in the group. You just send that one. Okay, I think we should start. So let's have a recap on what we saw during the past 2 days. If you close the door. In the first day, we started with the overall idea of deep neural networks, in which we saw basically we had a set of neurons. Each of them was first a linear combination on their inputs, and there was an activation function that added the nonlinearity. The nonlinearity in each neuron, in each cell of this network, allowed us to compose different mathematical functions that were not possible with simple matrix multiplication or simple linear approaches. And thus, as a result, we were able to model very different functions that could apply to a lot of different tasks in the world. Anytime when we have a lot of input data, for example, we have several we have a set of data, for example, a lot of features for a question, and we have an output label. We can always model it as a deep neural network. For example, you may have seen a lot of examples in the past 2 days, but imagine we want to predict the price of a house in a certain place by using a lot of features. For example, where is the area of the house, how big is the house, or what are the facilities, and all of them are the features. And the thing that you want to predict is the price of the house. Like if I want to purchase the house, how much should I pay? So in that case, all of the features would be the things that we pass to the input layer, and the output layer should give us the value of the price of the house. And we had also the hidden layers here, in which they do the big task of making the nonlinearity possible so that our model is trainable. You learn the concept of backpropagation, in which to train this model, by which we mean to find the weights of each of these edges, and basically to find all of the connections here, we put the outputs of the data that we already had, that we call it the training data, into the network, and we run the backpropagation algorithm that would give us the value of the weight. We run it on the training data, and then when we are done with updating the weights at each step, we then go to the test data and just put the input of the test data into the input layer, find what is the output, and then compare them together using a metric. For example, you can find how many match, what is the mean squared error between the output layer of the network and the correct values, and so on. And an important consideration was that training data and testing data should always be kept separate, because if you mix them, you are updating the weights based on what you see in the test data, and thus the evaluation is not a correct evaluation of how your network would do in a real world environment. So that's something that we should always take care of. This is just a recap. You know something, just wanted to do it because we have to. Then you saw CNNs, convolutional neural networks. So basically mostly done in the concept of images. You have your input image, which you have a certain data structure to start with. And then you have convolutional and pooling layers, which you have already seen yesterday, I assume, which do the feature extraction, by which we mean they find data from the raw values of the input image that can be useful for the classification. Because normally you can also convert an input image into a long set of values and just put it into a network. But it might not be as effective, because images are not only a set of random values. Images have meanings. There are specific parts in each image. For example, imagine this image of a classroom. The individual pixels have meaning. Like, for example, when you see a whiteboard, the whole region of the whiteboard means something. It's not that a specific pixel values mean anything. So by using the convolutional layer and the pooling layer, we are extracting featured or importance values of a picture, of an image. And then when we have those, there are a bunch of numbers. We just flatten them. By flatten, we mean we convert them to a kind of vector or something like that. And then we put it to a normal neural network that we had. From now, we can call it a multi-layer perceptron or fully connected layer, or anything that you would like to call it. And then we arrive at the outputs. What does this tell us? You could have just used a normal neural network, like just the last thing that you see with the colorful dots there. However, because our data was in a certain way, researchers found a way to first convert the raw data into something and then use that something for the network. And this actually happens a lot, because otherwise the last 2 sessions were just enough for you to understand the whole world of deep learning. But it's not, because for each specific data type, there are ways to first convert and pre-process it to a format that the final fully connected layer neural network could understand better. Here in this example, we are just using convolutional layer and pooling layer to do it. But for another type of data, which we will cover one today, and which will cover, I think, 2 others next week, or at least 1 other next week, you see that before passing it to a neural network, it's better to do some pre-processing to ensure your data is in a valid way. Any questions on the general concept? I think it's pretty easy, right? Cool. So now that's what I wanted to say. Now we want to introduce a new task. Our task until now were just a set of features that were valid at the same time And we just use those features to predict an output. As I said, like features like area of the house or the place that is built in or like the age of the house. And then the output was, for example, the price of the house that you should pay for purchasing. There are also other types of data. One of the very common types of data you find in real world, and you find in a lot of different places, is called time series. What is time series? You may already know, but for those of you who don't know, time series is data that is measured at regular intervals, step by step. Anything that comes with a timestamp for each step is basically a time series data. For example, imagine you want to make a weather app and you want to predict the temperature of a city for tomorrow. This is exactly time series data because you have the temperature per hour over the past few weeks or months or years or anything, and you want to predict the next step in time. So this is an example of time series data, hourly temperature in a city. Or you want to predict how much would be the height of an ocean tide, just based on the data from previous times. So it's again time series, which are useful for weather tasks. Another thing could be for healthcare things. For example, if you want to predict heartbeats, not necessarily might want to predict heartbeats, but still it's a type of time series. It can have usage in finance. For example, the stock price of a company could be modeled as a time series. Not that it can be solved by just converting to a time series, but the nature of the data is per time. So you have one data point per time, so it's time series. Another one that we will actually have our real world data set that we will code today is, for example, you want to, there's a chat. Someone has typed something, sorry. So in time series, you have only one feature to train on? No, we will actually have it in the next session. We will see that you can concatenate features. But the thing is, one of the features is time. Like the only important thing here is that one of the features is time, and it changed with time. And so it introduced new things, like you can't go back in time, right? So you can find patterns in time, and that's the main difference of time series. It doesn't necessarily to only have one feature. We'll talk about it in the next part. Maybe just, let's say here, answers of a student to exam questions. Imagine you want to build a tutoring system. You want to predict if the student would answer a question correctly or not. Again, here you can have multiple input. Like you can have the title of the question, the topic of the question, the difficulty level of the question, the time spent on the question. Like all of them are different features that you can use. But in the end, it's like one after other. You answer the question. So it's a time series. And a very important task that will be the focus for one of the sessions next week is text. Like imagine you want to work with textual data. Like people have submitted something and you want to predict if, for example, the text is a positive sentiment or a negative sentiment. Any kind of data that works with text. Text is also time series data. Like see, for example, we can say EPFL I like EPFL. They both have the same words. The only difference is the order that they come. And we can also consider the order as time and model it as time series, which we will do next week and you will see. Any questions? So I think you understood the task pretty well. Maybe I spent a lot of time on this, but yeah. You can also do two tasks after you have a time series data. You can either do classification. For example, in the written text, you have a time series of the word that people have written over time, and you want to, in the end, say if the sentence is a positive sentence or a negative sentence. For example, if they write, I like EPFL, you say it's positive. If they write, I hate EPFL, then it's negative. So it's classification. You can also do the task of forecasting. By forecasting, it means just predict the next value. Like the temperature example, you have the set of temperature of weather in a city, like in Lausanne, and you want to predict what the temperature would be next hour. So now you are doing forecasting or prediction. So both tasks are possible in time series data. One tip to find if you can model data using time series is that if you see that the meaning of the data changes by changing the order or permutation, then it's a time series data. For temperature is easy, but for text, it might not be very obvious that it's time series. But if you change the order of the words, the meaning of the sentence can change, or at least it can become a weird sentence, which means that the semantics are changing. So it can be considered a time series data. Any questions? If I'm going too fast or slow, just let me know because I tend to speak a bit fast, not a bit fast, but very fast. So just let me know whenever I need to slow down. So is classifying or forecasting time series data obvious? If it was obvious, I wouldn't have covered today. So no, the model needs to extract trends, cycles, rises and falls. and basically something, because it's related to time, so we need a specific models, or at least a part specific in the general idea that you had to work with time series data the best. Now that we know what's time series data, we can think why neural networks might not be the best approach to tackle time series. The answer is they do not have memory. What does that mean? In neural networks, the processing of each input data, each input entry, happens independently of the others. Like you can see here, the three input data, like the three features, for example, the price, the area of the house, the facilities, anything, are independent of each other and are put parallelly to the model. We should flatten the whole data. However, time series data naturally comes gradually. And the researchers had an idea, what if in our network, we can have an internal state that changes over time and is constantly updated. And maybe if we have such a state, we can update it over time so that it models time better. Not that we can't model time using neural networks. If you have a big enough neural network, you can still model time, but we are just thinking how to improve it. Neural networks inherently do not have memory. So we want to introduce memory into neural networks. Any questions? Fine. So we enter recurrent neural networks, which is the main topic of today. We have an input layer, and we have the output layer here, just one dot, but it can be multiple. And then we have the hidden layers have a recurrence. The output of the layer is again sent back to the input. And that's the main difference you have compared to a normal neural network. In the normal neural network, the path to go is always from the beginning to the end, as you can see here. You don't have returns in the network. However, researchers thought that maybe for time series data, for data that changes over time, it's better to have recurrence so that the model can update itself after each time step. Basically, update the internal value after each time. Any questions on the idea? Fine. How does that work in practice? Let's see together. So this is the basic architecture of a recurrent neural network. We have the input output and the recurrence is to back. But we know that in practice, we can't connect the output to the input, right? Because they can't be processed simultaneously. The output still depends on the input, and input depends on the output. So this would make a weird mathematical formula. We can't do that. So in practice, how we design it is that we unroll the node over time. We basically split it into a lot of nodes that are similar to each other and are connected after each other. So it's like this. We have the input that's always there, because this is just one of the cells that we just unrolled it over time. We have the input that is connected to every state. Each state corresponds to one time. Like this is, for example, for time t equals 1, t equals 2, t equals 3, and so on. We have the input that goes to each state. We have, of course, the outputs that come out from each step, and the output of each step is also an input to the next. So you can see here, for the first one, imagine we don't have this. We just have the input and there's an output, but the output not only goes to the main output that we have, also it's passed to the next one as a combination with the input. So in practice, it's a weighted average. You can consider it as a weighted average of these two values, as you can see there. So how it works? You remember, in a simple neural cell or neuron, we just had a weight times the input, and then you put it into the activation function, which could be a sigmoid. Here, we also add plus u times this state. So this is the new thing. So we not only, the output of the network does not only depend on the input, as we just said, but also depends on the state, which is actually the output from the previous node. And then you add the bias term as well. So here, W and the UO are basically matrices that you basically use them to make a weighted average of the vectors of input and the state. And you add a bias vector as well, which is, I think you have already seen what's the role of the bias vector. If not, let me know. Then you pass it through the activation function, which can be a sigmoid or tangent or anything like that. And then you produce the output, and this repeats over and over. You may already find a major limitation of this, which is indeed a major limitation of this is that the output, the input depends on the output of the previous cells. So you should run all the cells, and this can be time consuming and resource intensive that we'll cover in more detail tomorrow. But that's the whole idea. Any questions about this? Like how we unroll the RNN? Fine. I assume it's fine, but again, let me know if I'm too fast or too slow. Okay, I think I'll put the code in the end. Like I decided to change it last minute. I will have a full code in the end. So for now, we'll just go over the concept. But so we saw RNNs include a hidden, we call it also hidden state or memory state. Those are the same. Like basically, that's the value that you add from each cell to the next. They include that over time and they remember information about sequences. So RNN are useful for working with sequential data. And that's why we are using it for time series data, because time series is sequential in practice. And also for text. So a lot of tasks in NLP, natural language processing, that work with text, a couple of years ago, were all done using RNN. RNNs were the best model that would have worked with text. Now they are not. Now they are transformer, which is the best model that we'll cover tomorrow. But now RNNs are not the best thing, but it's a useful thing to know in order to progress in the domain of deep learning, because they have sequence matching. Now I have one conceptual question from you. Before that, let's again see it here. So this is another way of visualizing an RNN. This is each layer. We have the input. We have the input here. We have, first of all, the internal state. In the beginning is H0. You can initialize it to some random vector, anything. You have a hidden state. You pass the input, you produce output. It also produces another output to the next state. And then you again use an input here and you produce an output and so on. So at each state, you have the internal state and the output, and that goes over time. In the end, when everything finishes, you have a set of output here that you can use. For example, you can feed them to a normal neural network to predict or to classify or to do anything you want. The main difference here is that y1 only depends on x1. y2 depends on x2 and x1, because we have also input from here. y3 depends on x3, x2, and x1, and so on. Now you might get why it is useful for time series, because if we have a time series, we can never go forward in time. So it doesn't make sense if we predict something based on future timestamps. It's always useful to predict based on what we saw previously. And that's what exactly RNNs do. Because here, each output only depends on its own input and everything before. It doesn't depend on everything after. And that's what makes RNNs successful, because they naturally encode the fundamental measure of time, which means we can only go forward and not back. Fine. Okay. Then there's also the formula there. So this is how in practice it is applied. You have in each step, you have the input. X of t is the input. I'm talking a bit louder now because the microphone is there. X of t is the input. And then we have a weight for the input, and h of t minus 1 is the hidden state output of the previous node. And there's also another weight associated with that. And we basically make a weighted average of these. Actually, these are math presets because these are vector operations, right? But in practice, it's like doing a weighted average. And then we basically, this would be the outcome of each state, which we will put into the activation function. So here we have used a tangent hyperbolic function, but you can use also other functions in practice, like sigmoid, but mostly basically in RNN they use the tangent h. And then you predict at each time, you again multiply it by a certain matrix, and then you do a softmax, which we'll talk about later. So they just function. You can just assume it's a function of the output. This is just a general mathematical formula. I didn't go into deep details on why tangent h works or what softmax. We'll talk about them later. But this is generally, conceptually, how it works, and we'll see it in code later. Any questions? Fine. So now question for you, which is quite easy, but just to add some interactiveness. Imagine you have an RNN, and you are working in a company, and you are making a keyboard for Android or iOS, like a keyboard that people can use, and you want to add an autocomplete feature to the keyboard, so that when people are typing, they see the next suggestion. How do you think you can make it with an RNN? Anyone has an idea? Don't be shy, just say something, it's fine. Imagine you want to make autocomplete. You know autocomplete, right? Just it says you, for example, I'm writing I am doing, and the next suggestion is bad. How do you make an autocomplete system using an RNN? Yeah, so exactly. So in more details, you consider each word as a one step at a time. So first of all, you should train the model, right? So basically, I wanted to do it from a bit earlier. How do you make such a model? Not how do you use it in practice? Like how do you train that model? Yeah, exactly. So the one idea is that we just pick random text on the internet and we use them as the time series data. Basically, for example, I just pick random text from the internet. For example, I am Parsa, and just put them in the inputs. And then you know the outputs as well. Like each step you should predict the next word. And I train an RNN with it to just predict the word. For now, you can consider words as integers. I will talk about how do you map words to integers. That's for next week. But for now, you can consider each word as a single number, and you just predict the numbers. And then in a real system, you have the RNN trained. I am typing, I am doing. You just pass I am doing, and then check the output here. This should be corresponding to the number that represents the word well. So you provide just well as a suggestion to the user. This works because text is a time series data. And actually, people have been using RNNs for this a while ago. So it's not something just made up. People have been using RNNs for this, but not nowadays. So any questions? All fine? Fine. Yeah. Yeah, I thought if you know RNNs, it might be a bit easy for you, but still, I think we should go over this in theory. It's being recorded, so people might see and they not know. Okay. There is one issue with RNNs. We call it the vanishing gradient problem. So basically, when you do the back propagation in such a long network, because the network is very long, that's the difference, right? In a normal neural network, you usually have like, I don't know, 2 layers, 3 layers, 10 layers, 20 layers, anything. Here, it can be very long. Like imagine you want to do RNN on text. A sentence or a paragraph could have a lot of words. Or if you want to work with full documents, like for example, classifying a Wikipedia page, it has like, I don't know, maybe 10,000 words or something, right? So there are a lot of words. So it would be a lot of cells. And we know that in back propagation, maybe I will not go over the math, but you do basically derivatives with chain rule, with the chain rule. And a problem about derivatives is that using multiple chain rule operations would lead to very, very, very small numbers because each of them is less than one. And if you multiply a number which is less than one a lot of times, it would be almost close to zero. So the gradient that you will use to update the weights of your model would be practically close to zero. And thus for long sequences, which can be text or like long temporal data or anything like that, basically the gradients, we call it, they vanish. Or they can also explode. Like if the gradients are big, in theory, if you multiply a lot of them, the gradient explodes. So basically, when you multiply a lot of things together, it's not very useful to use an RNN. It also makes it difficult for RNNs to predict based on the entries that occur a long time ago in the sequence. Because for those entries, the gradient would practically be zero. And we have almost no weight update. For example, here, you want to imagine like there is a text that people are writing. And again, the autocomplete example. In the beginning of the text, they write, I grew up in France. And then they continue talking about a lot of other things, a long, long text. And then they write, I speak fluent. And then they want to say the name of the language that they speak fluently. Of course, you may think a good suggestion would be French. But the model, if it forgets what's happened in the past, because of the vanishing gradient problem and also other problems that RNNs have, it tends to forget things that occurred at the start of the long sequence. We call it that they don't have maybe very well long-term dependencies. So you can't model long-term dependencies. And maybe here, the effect of France on the weight here is almost nothing. And thus the model would not be easily able to say French is the correct completion, which is not very nice, specifically for long time sequence data. Do you understand this problem? Okay. So researchers were looking to find ways to circumvent this, of course. We will cover one of them a bit today. So, and then we'll also see another one that will solve this tomorrow. So this was an RNN. Again, we had the inputs, we had the hidden layers, and we will pass them together, and we'll use the outputs. As you can see, now we have the vanishing gradient problem because each of these steps is derivative, all of them using the chain rule. And basically, this would have no effect on xt plus 2 here. That was the problem. When you zoom in on how an RNN was made, it is the inside of each cell, right? So we had the input, we had the tangent H that would just accept the value from just the prior cell and continue. And you may now find what's the problem here. The inputs, I mean, this is just constant, right? This is not something that you optimize for because the input is given by the user. You only optimize on the weights. But this is something that you can optimize for, and this is what makes the problem because the only other link apart from this that goes inside the RNN cell is just from the previous cell. So an idea was that, what if we add another input to the RNN cell that directly comes from earlier parts of this sequence without needing to pass through the tangent H each time? Because this is what makes the problem. You make the derivative of the tangent H, and that would make the whole problem of vanishing gradient. So if we can somehow skip the tangent H and just pass the value that we had earlier to the RNN cell, it might be useful for solving this problem. And it turned out to be true. So what we are showing now is basically the concept of LSTMs. So what's an LSTM? It's now very more complex here. This is one of the cool ideas that were able to help a lot in improving the vanishing gradient problem of the RNNs, which is quite nice. So let's see how it works. You remember previously we just had the tangent H just from the previous output and the previous hidden state and the input. Oh, sorry. Here it's different. So in each cell, we do two things at the same time, basically. We have one row on the top that does not pass through any tangent H, if you see. Like there's just a multiplication there and just a plus there. And basically that line could ideally transfer the input without passing through a tangent H to the next cell. And that's what we wanted, because we wanted also to have a path that does not go through any kind of function that would make problems in the derivatives. You may think there's still a tangent H there, because here we are using tangent H as an input. But the thing is, you can control how much is the addition, like what's the weight of this part and this part. You can control the weights so that you can control the problem of vanishing gradient. And that's something that allows us to do. We'll see the formula next. But I wanted to just give you the idea. At the same time, we also have a couple of other functions that we apply here. For example, using the input and using the normal output as we had previously from the previous cell, we calculate the values that should go here, the values that should go here, and the values that should go here. And ultimately, this value, which is also a tangent H of that value, goes to the next cell. So we both keep what we already had in RNN, but we also add some tricks, some workarounds, so that whenever we want to limit the effect of the nonlinear function, we can do it. Fine. You got the general idea. I will see the formula now, but if you got the general idea, let me know. The important thing to know is that this is not just a plus, just you sum them together. It's a weighted sum. So you control the weight yourself. You can control how much of the weight comes directly from the previous cell, how much comes from previous cell input to a nonlinear function. So you can control it yourself to fix this problem. So yeah, let's see the components of the LSTM step by step, and then we'll see also another architecture, and then we will directly go to coding. So what is the cell state? Cell state is one of the components, which is the line that I told you. It's the top line that runs in the whole chain, in which information we have in the network can flow even without any changes, because ideally we can set the weight of here to 0, and we can set the weight of here, weight of here to 0, and weight of here to maybe something, basically, yeah, to 0 to cancel them. Here it should be 1. I think we set this value to 1 and set this value to 0 so that you basically cancel them. You can control how much info is transferred from this line, and you can add or remove data. You can add or remove, because it can be also negative, data to the cell state via the gates that we have here. We call them gates. Why is it a gate? Because you can control how much flow of information is passing through it. So we call it a gate. Basically, it's usually output of a sigmoid. So it can be 0, which means let nothing go, or it can be 1, which means let everything go. And that's how you control how much of the data comes from the nonlinearity and how much of the data comes directly from the previous cell state. You might think, when I make an RNN, should I control all of these myself? Should I put values for the way, like how much should it go or not go, all of these myself? The answer is no, because you can use all of them as a parameter that will be learned automatically in the backpropagation algorithm. So in practice, you just make these parameters all as trainable parameters in your PyTorch model, and just let the PyTorch framework do the backpropagation for you and find optimal values to all of this. So you don't need to find values for the weights yourself. Any questions? Fine. I hope it's clear enough. Again, let me know if it's not. So that's how you make the cell state. We have different things that all contribute to the output of the cell state and contribute to the output as well. So let's see with the first part. This was the output from the previous cell, the hidden state from previous cell, and this is the input of this time. So it's ht of -1. This is x of t of this time. First thing is, we call it the forget gate. Forget gate means that we want to see, when we see a new subject in the sentence, should we do the forgetting or not? We call it forget gate because in practice, it's like when you see a new subject, to forget it or not. But in practice, they don't mean anything. Like it's a forget gate, so it's just about forgetting. It's just a mathematical expression. So what it does is that it applies a matrix function on basically a linear combination of these two inputs, adds the bias, and passes it through a sigmoid. So this is the first input here. We call it f of t. Just called a forget gate because they love to call it, but it doesn't mean it's necessarily regarding forgetting something. Then we have something called the input gate, which has the role of saying what new information we are going to store at the cell state. You may think, okay, but this is the same thing, again, a combination of the inputs. Why is it different from a forget gate? Why do we call it forget and why do we call it input? Because forget could lead to 0. And then when you zero this, when it's multiplied by this, we are basically forgetting everything that has been done. So this, because it's a multiplication, you have the power to forget. How could it be useful? Imagine you are writing a text and the person who is speaking changes. For example, it's the dialogue between two people. One of them speaks French and one of them speaks English. And you want to provide autocomplete suggestions that is relevant to the current person. So maybe the model can learn to forget whenever the role changes, like whenever you go to the next line, which means the other person is speaking. If you want to forget something, you should the model should be trained such that f of t would be 0, and thus it would be multiplied by everything there, and it would output 0. So basically, it forgets everything that has been learned until now. Sometimes it's useful, just saying. But for input gate, which is here, you have a sum here. So basically, anything that you calculate is gonna be added to the cell state. And the role of the input gate here is to see what new information you are going to store, because when you are going forward in a time series or in a text data, you are seeing new stuff and you want to add them. For example, I lived in France. Whenever you see the word France, you want to add it to the cell state so that later you can say they should speak French. How do you do it? You calculate an I of t, which is very similar to f of t. Basically, it's the same formula, but with a different weight. So it's wi, over there it was wf. It is just a different weight, but it's still output of a sigmoid. And you also calculate, again, a very similar thing with a different weight, but with the tangent h function. You may think why they used first the sigmoid, then the tangent h and something. It just worked well in practice. Most of them do not have very theory backgrounds. Like, why this really worked? And yeah, maybe you can replace it with another function and it would just work as well. So in practice, it's not a big deal. But you have both of them, you multiply them together, and then you add whatever value you receive into the cell state. Fine? Any questions? So after running these two steps, you have an f of t and you have an I of t, and you have the c tilde of t. So you have 3 values. Basically, as you can see here, t of t minus 1 is the previous cell state. It's first multiplied by f of t. Then you sum it with I of t multiplies c tilde of t. So you have all the values. You have calculated them from the sigmoid and tangent h functions, and you just sum them together. Here, you do not have any trainable weight. So you do not have any weight that could be trained in backpropagation, because all of those weights were already considered here, here, and here. We had three weight matrices that you wanted to predict. Fine. Now we have, so after this step, we have the final cell state, and that just passes through the next state and makes our problem fixed. We also need to have the output, because anyways we need to have the output. We are not removing RNNs after all, it's just a variation of the RNN. So we use a pretty similar technique here. We use the sigmoid as we had in a normal RNN based on the S of t minus 1 and X of t. Again, there is another weight here. W of O is yet another weight. However, the whole idea of LSTM was that you can use the ongoing cell states to help you find the possible output. So we also need to calculate it at some point in the output. So we pass the cell state through a tangent H, and we multiply it by the output that we have from this two here. So basically, O of t would be the sigmoid of a matrix times these two, a linear combination of these two plus the bias. And then the final H of t, which is the hidden state of this cell, is this O of t that we found times the tangent H of the cell state. So that's how it's applied in practice. Again, you don't need to memorize any of these formula. In practice, you will just write a PyTorch code that will do, it will import LSTM and RNN, and it will work. But just to have an idea when you want to debug your model to see why it works, why it doesn't work, and things like this, usually having an intuition on the concepts could be really nice. We call it the output gate because it's still a kind of gate, as you may call it, because you have the weight and that can control how much of the output, how much output is influenced by the current value and how much from the steady state. So, any questions? Is all fine? Good. So again, I will keep the code in the end, but so we saw LSTM, right? There are problems with LSTMs. First of all, as you may have understood, the formulation is very weird and difficult, as it seems very made up. Like someone came with this idea and just tried to apply it in practice and it works. So there are also problems with it. Also, when you want to go into the deep mathematics to find the mathematical behaviors of these models, they are usually pretty difficult to manage because there are a lot of tangent H and sigmoid involved, and they're usually very difficult to simplify in long chains, and also difficult to calculate from a computational standpoint. Because imagine for each cell you have to calculate all of them, and it can be for a lot of cells for just one entry, one time series entry, and that happens for all of your training data, which is very, very weird. So it's difficult in principle to manage. We will see tomorrow approaches that helped to make this way easier. But for today, we are just introducing one other variation that a lot of people use. It's not visibly simpler than LSTM. It's still difficult to manage, but some people prefer it, which is the gated recurrent unit. So it's yet another variation of LSTM, of RNNs. Here, to make the things a bit more simplified, they combine the input and the forget gate into another gate that they call the update. Because ultimately, both have the same purpose. Forget says how much from the past information should we forget, and input says how much should we introduce a new information. So in practice, both are updating the cell state. It's different from output, right? Output gate did not update the cell state because it just output the previous that LSTM. But when you want to update the cell state, you use the forget and input. Here you use update gate. So how do you do it? Again, you don't need to memorize the formula. We are just covering them once so that if someone in the future asks you, you say that, oh, I know how GRE works. It's just like that. And in practice, you just code it. Sorry. So how do you do it? We have this Z of t, R of t, and H tilde of t. R of t is pretty simple. You just have the input, the previous, basically the previous hidden state and the current input, and you just multiply them by a matrix W of R and put them through sigma. Simple. For Z of t, we also do the same thing. So again, there's a sigmoid of the input, but with another matrix, which is W of Z. So it's basically another combination of the input and again put into a sigmoid. Then here, what we do gets a bit interesting. So we first calculate an h tilde of t, which is then used to update the main h of t, which is the steady state. H tilde of t is actually the tangent h of a combination of the input and the R value times the previous state. You may ask why this works. Like, I don't know how they came up with this. Like, I think they just played around with numbers until they found. So it's not something very valid, but in practice it works. So you calculate the tangent h, and then you have a weighted average of the current value that you calculated and the previous steady state, so that you can update it. And the value of the update is determined by z of t. So basically, z of t times the current h that we calculated plus 1 minus z of t times the previous h that we had. So you just have this formula, you apply them in a sequential way, and you have your GRE. Any comments, questions? Fine. So, yeah. So you can have a lot of, as I said, you can have a lot of variations, and one of them is GRU. So it doesn't mean that every RNN in the world should be either normal RNN or LSTM based or GRU. This doesn't make sense. But we are covering those that are most famous and most used in the literature. All of these also called the reset gate as well. Some people love to call it reset gate because it tries to change the hidden state, as you may see here, because it has directly effect. Like you can see, each time the past hidden state, right? So if R of t is 0, here, each time is multiplied by the previous hidden state, and it will basically erase the previous hidden state. So it's also called the reset gate because it can change the hidden state. And we also call it like to reset the short-term memory, or basically a lot of concepts that people in the literature love to call it. And we have also the update gate, which is updated for, as they say, long-term memory. Again, these are not real concepts like our human short-term or long-term memory. It just means that you reset it in the short term or you keep it for longer term so that you don't have the problem of vanishing gradients. It's just a concept. If you heard the word long-term and short-term memory, it basically means reset and update gate. Sorry, update and reset gate. So yeah. Yes. Oh, okay. So 1 minus is literally 1 minus this cell. So as you see here, it's the same. So it's a linear. We want to have a weighted combination of the h of t that we calculated. Actually, I don't know why the 1 minus is there. 1 minus z of, yeah, it's fine. Okay. Yeah, it here means that this is z of t. And here would be 1 minus z of t. So it would be 1 minus z of t times h of t minus 1 plus z of t times h tilde t. So it's literally showing that formulation. And why would you do the 1 minus? It's just a weighted average of h tilde t and h of t minus 1. Basically, the weight is z of t. And the other one is 1 minus z of t so that you make the average possible. So the bigger that one, the smaller this one would be. So it's a trade-off between the current state and the previous state. Right? Yeah. It's just a trade-off, right? So the more z of t is, the more you put focus on the current h tilde of t, and the less you would keep focus on the h of t minus 1 that you had, so that it can be adapted for the different task, specifically regarding the vanishing gradient problem. So again, for the code, I will talk later. So let's have a recap, and then we can have a short break, and then I'll go to code. But maybe we can even finish it earlier. So as we saw, LSTMs and GRUs can help. I don't say they mitigate totally or they fix it totally, but can help fix the vanishing gradient problem. So there are just two architectures that we introduced that can be useful depending on reality. And the main thing that they were used a lot were for text. They are very useful for text, and we'll cover it in more details for the NLP lecture that I think we'll have next week. Because for text, you can't just get text as a time series data and just put it into an RNN or any other model to work. You need to convert the words into numbers. You can say, okay, I just assign a number to each word and so on. But in practice, there are better ways to do it, for example, such as embeddings, that we'll cover in more details, how you should deal with text data. There is one main concern that a lot of people have with RNNs, is that because of all these weird mathematical formulations that we have here and all the hidden things that are going in, they do not have necessarily a meaning. For example, imagine in a certain cell, the value of h tilde of t is 0.7. It doesn't mean anything. Like, you can't extract meaning out of it necessarily. So imagine you want to make a system that is interpretable or explainable. You want to for example, the user of the system to know why your model has predicted something, not to only know the result, but the reason behind it. Usually such models, and in general, most of neural networks are not very well at this task because they do a lot of magic tricks in a sense from their hidden layers, and they are not necessarily interpretable. To some extent they are, and there are ways that people have tried to make neural networks interpretable, but this is always a struggle. Specifically for RNNs, the formulation, and for LSTMs even worse, the formulation is so weird and so complex, and weird but complex, actually, that it's very difficult to interpret. And as a result, you can't tell a user or a person who is using your model in a real system on why you made the prediction. And this is actually very important. In a lot of places, you want to do it. Imagine you're working with Grammarly, and it tells you have a grammar error here. You need to know what is the why it made the error. Otherwise, you can't fix it. If you just highlighted in red and it provided no suggestion for you, it would not be useful. I mean, it's a different topic, but I'm just telling why interpretability, explainability, and all of this could be important in a real system. And these are all challenges that you need to consider when you want to deploy or put a neural network-based thing, such as RNN, LSTMs, GRU, and so on, in a real-world environment. The next natural step after people worked with RNNs were attention mechanism, which we will consider tomorrow, and transformers. They are all ways that people have tried to improve the problems that RNNs had, specifically including the long-term dependencies. We'll cover them in details tomorrow because I think the vote was that we split it into 2 days. So we'll try to keep the session a bit shorter. And then with all of that, we will go next week to see how we can apply them in real practice, for example, for NLP. So now I think the time is pretty fine, 4:59, it's almost 5. We can have a quick break, and after that we'll come to coding. So we will try to use a real data, like a real almost real data, to train an RNN to see if we can predict in a real case solution, and we'll basically write the code from scratch together, if that's fine with you. Any questions? Yes.
In general, it might be a longer topic to discuss. How have people tried to incorporate interpretability into arguments? Perhaps they change.
Yeah. So in RNNs specifically, so I know mostly about the newer approaches, but so in general, in neural networks, specifically the components that you add before the final layer could be interpretable. For example, in CNNs, when you extract batches of images, you can sometimes visualize it. Or also with transformers, we will see in the attention mechanism, attention is basically very quickly weights that you assign to different combinations of the inputs. And we will actually see one example tomorrow that how you can visualize it. So like you have some intuition of what's going on. But ultimately, for the hidden states, they usually have no meaning. So any kind of interpretability that you do is, for example, you may know decision trees. I don't know if you know them. Decision trees are a kind of more traditional ML approach, machine learning approach. It basically say, okay, if it is more than this, you go this route and that route, and then you make whole tree to predict. For those, it's like super transparent because you can even a human could follow. But here, a human can't follow other than just calculating the stuff. So it's by in nature not interpretable, but in practice they have a way to it. Actually, in the last offer of this bootcamp, we had one session on explainability. We had literally one hour session in which we invited a PhD student who was expert in explainability to explain that. I don't know if this year we would have it. I don't think so because she was not available anymore. But I think she was not available for this week. But let's see what happens. Like in theory, this can be possible. And I'm not an expert in this, but I will show you some examples tomorrow as well. Yes. You have a question? Oh, sorry. Fine. So with that said, if you don't have any questions, maybe let's have a quick break. Because you voted for having 2 sessions so that each of them is not too long. So I will try to. So we now learned about our RNN, LSTM, and GR rules in the past hour. Now we want to get into doing one real example, and let's code that together so that we see how it's coded in PyTorch, and basically we see the problem that can come up. Our real case study here is a time series data again. We call it the task of student knowledge tracing. I use this example because it's also very easy to understand usually. So imagine you have a learning system like Moodle or Coursera or this kind of thing that you pass courses in and you have exams to do. And a student interact with the system over time and answer different questions. As I said, imagine there are assignments in a massive online open course or something like this that students answer questions over time. And of course, they answer questions of certain topics right or wrong over time. We want to see if we can predict their answers to the next question that is coming up to see if they will answer it correctly or wrongly, right or wrong. First of all, this is a time series task, right? Because you are answering questions step by step and they come sequentially. So the answer of each question does not depend on the answers of the future questions because you have not seen them. But it depends on the prior questions. For example, if you have learned questions from a certain topic or from a certain difficulty level, it's highly likely that you will answer the question correct again. Or if you have answered it wrong, it's maybe more likely that you answer it wrong again and so on. So this is the time series data exactly that we might want to predict the answers to the next questions from their history of the interaction with a set of questions. Why this is useful? Like this has been explored in a lot of papers. Actually turned out to be a useful task because in a system you can predict the probability of a student answering question right or wrong, and based on that you can provide questions into your exam that has the maximum learning gain for the student. Like you don't provide them with repetitive questions that makes them bored, but you provide them with questions that are more exciting for them and they're more likely to make it wrong so that in a real exam they won't make it wrong. This is the general idea behind the concept of knowledge tracing. You got the task that you want to solve, right? It's not very, it's just a time series data. And researchers have explored a lot of models such as Markov models, Bayesian models, and a lot of different things previously to predict if a student master each skill, they get proficient at each skill or not. And then also there have been researchers that have achieved the state of the art at the time results with just using LSTMs. So it means that using LSTM or using RNN, basically any type of approach that model time series data, is also useful for knowledge tracing. As you can see some results here, they have the DKT is the model that they announced, that they introduced. This was the first model using an RNN, using an LSTM for the task of knowledge tracing, and you can see it had improvement over most traditional. So it means that indeed it's the time series data, and you can model this using an RNN. So let's do it with code. Let's just open code and just start doing it. So I have a data here. Maybe I should make it a bit bigger so that you can see it here. So here I will describe it again a bit slower because people made this comment. Thank you. I don't know why the chat it should notify me somehow, but weird. Okay, I will describe it again. So in the beginning, for online people, we had a train data that was the knowledge that was basically a set of question IDs, set of answers, set of difficulties for each student. And we want to predict the last answer based on the previous answers and the previous difficulties. So that's what we want to do. This is the training data. We wanted to predict and using an RNN. So we first imported the data by using JSON and pandas. We just loaded it and we converted to data frame, and which is very, very simple code, like basic pandas code. And as you can see, there is the head of the training data, and you can see just the student ID, the question IDs, answers, and difficulties. You can also use the hint, but we are not using hints for now. Then we import test data, exact same code, but we replace train with test. We load it into a data frame, and that's the data that we have. So I assume everything is right until now. I hope. Fine. If not, please let me online know, right? Because I totally missed it. Sorry. Then we have wrote our specific dataset class to be able to load the data into the format that is useful for PyTorch. So whenever you define a dataset class, you define three methods: the initializer, which basically loads the data from the data frame and populates our class. We have the len method, which returns the length of the data set, so useful for PyTorch to know, and also the getItem method, which converts whatever index we want into a torch tensor and returns it to PyTorch to use. So first of all, for the initialization, we define our sequences and our labels. Sequences are basically our input data, labels are output data, X and Y. We iterate over the data frame. We find the answers of each student and the difficulties of each student. Ants and diff are basically two lists for each student, as you saw here. These answers, the list, and the difficulty also list. So we have two lists per student, and we add all of them in the sequence. So for each, basically we move them like this, that each element of the sequence is the ice element of answers array and ice element of this array concatenated together. That's how this line works. We only move to len -1, so we don't consider the last element because we want to use the last element to just basically do the prediction. If we also incorporate the last element into the training data, it would not make sense. So then we append that the last element only to the label and not the sequences, and we append what we made to the sequences array. So I assume all is fine. In the len, we just return the len of sequences because it's the len of our data. And for getItem, we just have the index here. We just pick the relevant sequence or label index, and we pass it to make it a torch tensor, and we just return it to the user. Oops. Any questions from online people, from offline people?
对，其实也可以啊，对，就这样啊，对，因为你不需要靠它的 library 的，对对对对，不需要写的，对你直接那个 run 也可以自己做。哦，这我记得另外说法还有别的用法，不过反正在这儿这 code 都自动生成，你也不用管它。
Perfect. So this is what we did. Now let's go to make the order.
Okay.
So again, now we have the data loaded, so we just go to class. We want to make our RNN. For example, I just call it our model. As you may already know, we should substance it from the torch.nn.module, which allows us to define a PyTorch network. Again, when you want to make a model, we usually have the initializer and the forward path. These are the two things that we make in our model. So first, about the init. I can maybe pass, for example, a hidden size parameter. Hidden size is basically the size of the hidden part. So usually, I don't know, we can put it usually a power of 2, but 64, I don't know, maybe 32, like this. And then you first call super init. What this does is that it makes the initializer of the torch module itself. So you always do it in the beginning. Then you define your RNN model. Torch.nn.rnn. Then you should define a set of parameters that would come with the RNN model. Actually, the RNN module in Torch allows you to not to deal with the mathematical formula and to just use the RNN as is, which is very nice. So we first provide an input size. Here, our input size is actually 2. Why 2? Because for each element, we have the difficulty and the... So here we had, right? We have the difficulty and the answer. So we have 2 elements per input. So basically, our input size is 2. Hidden size is hidden size. And for example, we can have any number of layers that we want, so 5 layers or anything like that. Or maybe we can remove it. I think the default is 1. Just keep it. And there is this for batching the input to the RNN that you basically put it to true. And then when we have this, so we have the RNN, it would give us the value of the output, but in the end, we want to predict one value. So because the RNN produces a lot of values as long as it's hidden size. So we want to only calculate one value. So we put one normal layer in the end. For example, a feed forward layer, which is just a linear layer. Maybe just call it ending layer, which is torch dot. So it's just a linear layer in the end that would map our hidden size, which is our 32, to only 1, because we need to only predict one value, true or false. is the classification if the student would answer the question correctly or not. Perfect. Then we should define the forward pass. So what do we do at each round? So first of all, we run the RNN on the input. So the output value would be equal to self.rnn of x, which is pretty. Here we ignore this value because we don't need the hidden state of the last layer. We are only caring about the output here. And then we should pass it again to the ending layer. So what we do is self.ending layer, and we just accept the suggestion. So what is this weird thing, colon -1 colon? It means that we select all of the elements of the batch. We select all of the hidden units, but here we just select the last time step of the sequence, because we only want to provide the last time step for the prediction. If for whatever reason we wanted to use one of the steps of the time of the middle of the RNN, we could have put normal numbers here, but -1 means that we want to use the last time step of the whole sequence. It's clear? Perfect. So now we defined our model, which is actually a simple RNN. Cool. So then with that said, let's go and use them. So let's see if there's anything online. Oh, someone's microphone is on, so it's not my problem. Fine. Okay. Cool. So oops. Let's go. So we want to first make our train data set. Perfect. It's automatically loaded it. Then we want to put it to the Torch data loader. We want to use data loader so that it can apply the batches. So we just say train loader. Let's accept Copilot suggestion. I think it's true, yes. So we just use the train data set. We can specify batch size. You already, I think, know about the batch thing. It means you provide multiple inputs to the model at the same time to save on computation and this kind of thing. And we can also shuffle the data so that any kind of effect of the data in a sample order is invalidated. Remember that shuffling does not change the order of the answers. That should not be possible. If the time series data, the order should be the same. It only shuffles between students, like for different sequences. Shuffles different sequences on itself, and it doesn't shuffle within its sequence. Perfect. Well, I didn't compile this. Oh, I changed the data set as a typo. Sorry. So I think now it should be fine. Perfect. So now we just define our model. Model equals our model. This is the RNN that we defined. And then we need to identify, as you we need to find, as you have already seen in the previous lectures, a loss function and an optimizer. So our loss function is okay. Which loss function do we want to use here? I think you have seen the MSE loss function. I think the minus per one. So here our task is classification. We want to do classification on whether the answer is correct or right. We don't care about the real values. Like, for example, if the model says with probability 0.7, the answer is right. Or if it says with probability of 0.9, the answer is right, it's both the same for us because we are predicting that the answer is right. So mostly for a lot of binary classification tasks, we use different kinds of things. For example, we can use binary cross entropy. I won't go into the deep mathematical things of that, but it's just you write torch.nn.bce with logit loss. It's a function that does this for you automatically. For many classification tasks, it's sometimes better to use this. If it was a prediction task of a value, like a temperature, maybe it's better to go with MSE or other loss approaches. Then you have the optimizer. You just use an Adam optimizer. I think you have seen that. You just use an optimizer that would work here, and you specify learning rate. For example, I don't know, like 0.001 or anything like that. Basically, this is a learning rate that you can play with also to see if there's any effect on the results. So, any questions? Fine. We defined the model, the loss function, and the optimizer. And it was able to run. So let's go. We want to now do the training. We need to specify how many epochs you want the model to train. I think you know the concept of epoch already. It's basically how many iterations we want to do the backprop. For example, I would say maybe 10, 20. In a range of 20, we want to maybe do it 20 times. Each time, we first go to training mode. What this does is that it allows PyTorch to see what are we changing in the model, what are we doing to the model, so that it can compute the derivatives and everything later. So by model.train, we are allowing PyTorch to be able to observe the behavior of our model. So we should move into the train loader. Maybe let's do it one step. So we just iterate over the train loader object that we found, which gives us at each time one batch. So maybe x and y are a bit misleading because x and y are actually not one data point. It's a batch. So maybe I can better write x batch and y batch, because in each step you get like 32 items or whatever the batch size was from the train loader. So first, you make the optimizer ready. I think you have already seen this. You call 0 grad on optimizer so that the optimizer is ready to be able to measure the derivative and everything here. You predict the output of the current model. In the beginning, it's an untrained model, but you will train it over time. You just call the model on the current batch and you call it the predictions. You usually call it ypred. This ypred is the prediction of the model at this epoch. Then you need to, what do you need to do next? Any suggestions? So now we predict the y batch from now. What do we do now? Like, how do we calculate? What do we do? Any ideas? Yeah, but before that, like we have to know what actually we should do the backward step, right? Because we are training the model. So it's a back propagation here. Yeah. Yeah. If we are no, we have not done prediction. So we are now training the model. We are in the training mode. We should compute the loss so that we can use it for back propagation. That's the idea. So we just calculate the loss. As you call, I will review the code again in the end, so no worries. The loss function of ypred and y batch. I think we should also squeeze the ypred so that it can be a vector. Basically, ypred could be like a multiple dimension vector, so we just squeeze it so that it's like comparable to y batch, and the loss function can work. It's basically remove the extra dimension of size 1. It's just something that you need to write. Then we do the backward step, and we optimize. We do the optimizer. That's it. So let's review the code again, in case you are not, you don't exactly remember how the training was done. For those of you who might not know, we have done everything until now. We defined the model, we defined the data. These were pretty simple. This is the important part. So we are running the training loop for 20 epochs. So this is just a loop. At each time, we first turn on the training mode. This allows PyTorch to be able to measure what we are doing. Then we iterate over the training data. At each step, when you want to train, we first call the optimizer to make sure it is ready. We use the current model at this step. This model is improving over time. We use the current model at this step to extract the output. Then this output is ideally very wrong at the first step, right? Because it's totally random output. But we calculate the loss between the output that we got and the real output. Y batch is the real data from our real data set. We calculate the loss function. Then we do the backward step and we step up the optimizer so that we can, by the back propagation, we can improve the model over time. This is what you always do when you want to improve a model, no matter if it is an RNN, an LSTM, a deep neural network, or anything like that. Basically, the only difference is that what this model is. The model here is our model, which was an RNN. It could be a different model in practice. All fine? We can actually even find the loss and print it. Let's do it. So for example, here, I will write, for example, total loss. We want to find the loss value. And here I add the value of the loss to this so that I can print what is the loss of each epoch. This is useful because we can see how the loss decreases over time. This is what we want. We want the loss to decrease over time, which means that our model is training. And because loss is a function of difference between ypred and y batch. So if loss is decreasing, it means ypred is getting closer and closer to y batch. And that means that we are trying to learn from the data, learn how ypred is being generated from x batch. All fine? So it's basically loss. And we just can now print it. So let's print epoch loss, total loss. Actually, we should, to make it relative, I think we should divide it by the length because the item is like a relative thing, but it's just for showing. So maybe let's run this to see how it works. Oops. Y pred. Weird. What's this? Non-type object has no attribute squeeze. Oops. Oh, we are not returning out here. Sorry, I forgot to write this. In the forward pass, you should return the value, right? If you're not returning nothing, so the output was non-type. Sorry. So do it again. Again. Define the model again. And now it's working. So as you can see, each epoch is running. And basically, as you can see, so it started with a loss of 0.64 relatively. It's going down and down, which means that the model is training. But it's stuck behind the point. And as you can even see, it sometimes gets worse. This is a sign of usually overfitting, right? You have seen the concept of overfitting already? Or no? You are all familiar with overfitting? Perfect. So it can be a sign of overfitting because the loss is increasing, but I mean, it depends on the case. Like it's not always overfitting, but so it you find the optimal number of epochs in your case, anyways. But this is how you do it. So we are not calculating loss per step, and you can even maybe put it in a plot or something to show it that our model is training well. So now we have the model trained. So now this model object, you can actually print the model and see it is an RNN with like this number of layers and an ending layer, which is actually a pretty nice representation. This model is now trained. So now it has weights that can predict the output based on the input data that we have. So let's try to run our test data with this model to see which accuracy we would get. Any questions until now? All fine? So if we do this, we are actually successful. And we can say that we have solved this problem. And we can then see which accuracy could we get from just a small data like that. So first of all, we need to load the data again. So we have already loaded trained data, like we just do it for test data set again. Our data set df test. This is exactly similar because the data is similar in type between training data and testing data. So we just use the same function, but with our test data frame. And then test loader is our data loader with the test data set, batch size of 32. And shuffle of false or true here with, it says shuffle false, so we just pick false so that we can, actually for test, it's usually useful to have shuffle false so that we know which entry corresponds to which output. So we don't shuffle them and we can like debug it here. So usually in test, you don't shuffle because it's not needed. You then go to evaluation mode. So you remember we had something model that trained here. This made the PyTorch think we are doing in the training mode, but here it's moved to the evaluation mode so that it knows it should not update weights. Let's keep all the preds and all the labels in an array. So labels are the true labels, and predictions would be the predictions from the model. And we want to compare them together, right? Perfect. So what we do, first of all, you should specify to Torch that you don't want any gradient updates. You write this with this sentence, with Torch.no grad. It means that anything that I do with the model should not affect the gradients. Why? Because we already have trained the model. We don't want to train the model on test data. That would be wrong. We just want to evaluate whatever we have on the test data. We want to simulate as like it's the real world model. And we don't want to update gradients with real world. We just want to test it to see how it works. So we write with Torch.no grad. Any questions? We'll open the chat as well. Nothing? So for x, y in maybe x batch. Right? We again open the batches from the test loader that we have. We put the batch to the model and do the squeeze. And maybe also, this is simple, right? We just put the batch that we have. Here, x batch is from the test data. We just put it into the model to be able to predict and also do the squeeze so that we can have it as a vector. So here, preds are the predictions for this batch of data. Any questions? We just put the model. So here, we are not training it because it's inside the no grad. We are just using the model to really get the output that the model would get for the current batch, which is from the testing data. Yes. So no grad here tells Torch that it should not improve the gradient values. Because if we don't write this, when we do this, basically Torch might think that we want to still we're training the model in a sense and of the gradients, but here we don't want to touch the model. So when you call the model, it just returns us the output. Yeah. I think it does the same actually. I think it does the same. I just I think it's redundant. I think model.eval should also do this. Yeah. So I don't think you need to write this if you write model.eval from what I remember. But in practice, I will write this to be honest. So yeah, I don't think it's necessary. You're right. So here we have the predictions. However, we want to have it so the predictions can be any value. We want to first cap it between 0 and 1 to get a probability to see if the probability is higher than a value or lower than a value. For example, we can say if it is higher than 0.5, we consider it as a correct value. If it is lower than 0.5, we consider it as a wrong value for like a student answering. Do you have any idea on top of your mind how we can convert a value to a value between 0 and 1? Do you have anything on top of your mind, any idea how we can convert a value to a value between 0 and 1? Like you have a number, you want to convert it to a number between 0 and 1. What function can you use? Exactly. So you can use some kind of normalization, right? You can use different kind of normalization. The thing is, you don't know what to normalize and what is the range. That's the challenge. Because we have not predicted for all of the values. You can also do for all of the values and normalize, but mostly in deep learning, what you do is you apply the sigmoid function, because it also does the same. If you look at the plot of the sigmoid function, it's always between 0 and 1. Maybe I can just show you. So yeah, sigmoid function is like this. The value is always between 0 and 1. So any value in the domain is mapped with something between 0 and 1. As you can see, this is the formula 1 over 1 plus e1 minus. This is something like a normalization, exactly. But because usually people do this, I mean, maybe normalization will also work, but people do this. So we just apply a sigmoid to map the value between 0 and 1 because we want to use it for classification. Remember that if we didn't want to use it for classification and we only wanted the output, we didn't need the sigmoid. Sigmoid gives us a kind of probability thing because probability is between 0 and 1. And then we can say, okay, if it is more than 0.5, we get a 1, otherwise we get a 0. So we want to just map it in a way. This is what is common practice. So you may want anything you do that. Okay, just let's append this to the all pred function and also append the true label. This is the true label of the test set to the all labels. So now after running this function, we have all the predictions and all the labels as values, right? And what we do here is just accept the suggestion of PyTorch. What does this cat function do? So here, when we add it to all preds, each time we are adding a list, right? Because pred at each step is a list of values because we are working with bashes. So cat function basically concatenates them all into a longer list. It's just a way to somehow flatten the whole list. So we have one long list of preds and one list of labels. Maybe we can print it to see how do they look like. Print all preds. You see, it's a long list of all values between 0 and 1. For example, here we have 0.6730, which means it is more than 0.5, so we can consider it as correct. Here we have 0.0028, which is less than 0.5, so we can consider it as a wrong answer, right? So that's how we convert all preds. And then you can also maybe convert all labels. You see here, these are real values. So because these are integer values, because they are from the ground truth data, right? So they're either 0 or 1. And you can now see if the model has got it correctly or not. For example, the first one, the model has got it wrong. Because the model says it's 1 more than, but it's 0. But for the second one, it got it correct. For the third one, it got it right, and so on. So because our model, of course, is not very accurate, like we can calculate the accuracy now. But in summary, it is wrong for some labels and correct for some other labels. Did you understand this, all of it? Like how we did the testing loop? Let's see if there are any questions online, I think. So we just did again the batching thing from the test loader. We put it to the model, we applied the sigmoid, and we appended the batch, and then we concatenated all of that together. So let's find the accuracy. Do you know scikit-learn? Any of you know scikit-learn? A bit. Okay. So scikit-learn is because some of you don't know, scikit-learn is a famous Python library for working with data, working with these kind of things. So we can use. There are a lot of functions also in scikit that are useful for basically finding accuracies, finding F1 scores, or any kind of metrics. You can just import them, like from sklearn.metrics, import, for example, accuracy score. There are a lot of different scores here. Maybe I can open it. So you see there are a lot of different things that you can calculate. Precision, recall, I don't know, there are a lot of things. F1, here, let's maybe start from just simple accuracy. Accuracy means how many we got correct divided by the total number. Like very, very simple, right? Then we can calculate the accuracy. So accuracy is very simple, actually. So maybe let's because it's a complex line, maybe let's write it step by step is better. So first of all, before getting to accuracy, we need to convert this into a Boolean 0 or 1. We need to check if it is more than 0.5 or not. So we just say the predicted is, just accept the suggestion. So what does this mean? It means that for any value of all preds which is less than 0.5, we consider it as true, otherwise false. It's just a Boolean. And then we converted it to a float. So true would be 1, false would be 0. All fine with you, this line? This is just a shortened way of I mean, it was Copilot's suggestion, but it was nice. So it's a shortened way of saying, just convert this expression to a Boolean, which is our true or false, and then convert it to float. Perfect. Then we just compute the accuracy equals accuracy of all levels predicted and print accuracy. 0.73. So it might seem like a high accuracy. I mean, not high, but we don't have an accuracy of 0.9 or something, but also consider that we only used 5 past prior entries of each student. Because in practice, you have a lot more data and you can make useful models. Even in the simple RNN, we had an accuracy of 0.73, which is indeed nice. However, so until now, did you understand everything? Is all fine? Now, a small challenge. Do you think this could be misleading, or do you think there's any problem with calculating accuracy like that you just count which one were true, which one were matching, and you divide them by all? Do you think there could be any problem? Like, what is the downside of this approach of calculating accuracy like this? I don't know actually if you have seen this in the prior lectures. I'm just assuming you haven't. Yeah, that's true. I mean, 0.5, we pick it because we assume it's mid-range. Imagine that's fine. Like, imagine we picked 0.5 as the mid-range. We have these two labels. Like, imagine we have predicted. Imagine we have these two. And we just want to find what is the optimal accuracy. Is this a good way to do that? To just calculate the accuracy score? Okay, let me then say the answer, because I think that might be difficult. Maybe just use this board. Imagine you have a data. You have a big data set. Like the same question answering thing. 90% of the questions are correct. Imagine you are like running this study in EPFL, and all the students are very experts, like you, and they already know the answer to most of the questions. So imagine in our data set, 90% of the answers are correct, and 10% are wrong. Now imagine your model does not work, and it just constantly replies correct to anything that you say. It does not do any mathematical anything, right? Imagine it's not trained. You just instead of your model, you just write return 1. Imagine that's your model. What would be the accuracy? 90%. And that's not good, because 90% is a high number. right? So we have always the accuracy score. There's one downside with the accuracy score is that in imbalanced data sets, in which there's no balance in the data, it's a very bad score to use because it gives high values, but in practice, it might mean nothing. Like 90% is the worst accuracy that you can have here. If you have 80%, it's actually worse than just return one, which is nothing. So in this data set, you should have an accuracy of 95. So accuracy is not a valid metric to use always. And still you find papers that use accuracy, unfortunately, even on unbalanced data. Like if your data is balanced, it's fine. But if it's unbalanced, it's not fine. So you should use other approaches. For example, I won't go into the mathematical definitions of all of them, but one thing that you can use is, for example, balanced accuracy, which is a variation of this that provides the average of recall over multiple classes. I won't go over the details, but you can use other metrics that does the work for you. So this was just a tip. Whenever you see accuracy in a paper, which is high, you should, or anywhere, you should check if the data is balanced or not. Let's check for our example, if the data is balanced or not. We can say the last answers is df test answers, and we want to only pick the last one. So what this line does is that for each row of the answers, we just pick the last element, which is the last answer that we want to predict, right? So last answers, when we print it, is actually a set of numbers corresponding to the last answer that people gave. And now we want to find the count of zeros and ones in data. So we just print last answer dot value counts. Let's see. So you can see we have an imbalance here. Class 0, we have 1,000, and class 1, we have around 2,000. So not double, a bit less than double, but class 1, we have way more correct answers than wrong answers. It's not as this example, like this was very extreme. It's not like that there's 9 times more, but it's still unbalanced. So it means that in our data, the accuracy score is not the valid score to calculate. So we should calculate another metric. For example, we can calculate the balanced accuracy from scalearn.metrics, import balanced accuracy score, and then balance the score. We just use the same line, all levels predicted, and we just print it. You see the balance accuracy is actually lower. It's still good. Like the balance accuracy of 0.5 would be something that's basically equivalent to random. So anything more than 0.5 is good. But you see that it's not maybe as fancy as the score that we had. Like if you tell your supervisor in the project that I got a balance accuracy of 0.64, they are not as happy as if you tell them I got the accuracy of 0.7 something. But this is the valid one because the data is imbalanced. So in practice, this is the real accuracy that we got on the data. Any questions? Yes? Yes. Yes, you can also use F1. Maybe let's just do it actually. From scale learn.metrics. F1 is another one. I didn't want to go over deep into the score because that one's not the goal of today. But yeah, let's just do it. And you should say the weighted average so that it can take into account the imbalance of the data. And just print it, 0.68, which is still, yeah. So this is another metric. F1 score is actually a metric based on precision and recall. I won't go into details on it, but you can read it later, or maybe I'll tomorrow or something like this. But yeah, so these are different metrics that you need to do. Just make sure you don't always do accuracy if the data is imbalanced. This is just the side point that I wanted to get you. It's not related to RNNs. It's valid for every deep learning or machine learning task. Fine. Any questions? Any other questions? If not, I think we are nice. And then we have only, I think, a couple of slides to quickly cover, and then I think we're done. So yes. Yes. I will put them in the, I will put it in the repo. Yeah. Yes.
I can ask it and then you tell me if you answer it later. For the optimizer,
Uh-huh.
can I which one where to choose the design?
Here. Yes.
Can you have more multiple optimizers for one model?
So in theory, yes. So maybe you can just define a different optimizer. And basically what the optimizer does is that it tries to update the model parameter so that it matches the value got from the backward path, the backward propagation, backpropagation. However, in practice, you use one optimizer because in theory it could work. Maybe we can try. Yes, exactly. The optimizer is updating weights because the parameters, which are actually the weights and biases of the model, also the bias. So maybe we can have another optimizer with this LR and then.
One optimizer and a subset of other.
Oh, good points. I've not tried that ever, but I think in practice it might be possible. But you need to, I think, change. You need to work with this object, and I've not done that to be honest myself. I don't think it's common practice, but yeah, maybe we can try even running this if you want. Let's see if it works. Just out of curiosity. So the last 6450 works. See how it works.
Within one optimizer, right?
No, it's not overwriting. So both of them are updated very separately, and they don't know that each other exists. They both use the weights. Actually, the behavior is very weird. You see, the loss is increasing. So it means that it's not working well, but because they are both trying to optimize in different ways, and then so the whole concept of the optimizer is that you have a function and you want to find the minimum, right? And the learning rate tells you how are you getting to the minimum. And if you have two different learning rates, two different optimizers, it can skip the minimum. Yeah. So that's why it doesn't work in practice, but in theory it's possible. Yeah. So anyway. So let's just remove this so that for the upload, there are not two optimizers. All right. So let's quickly go back to the slide and then wrap it up. There are two quick concepts that we wanted to just briefly touch today. They told us to briefly please also touch on this today. Two things that you also do, not only in RNNs, but also in other neural networks, to just basically make it ready for tomorrow, which we will explore them a bit more. What is batch normalization? So the models are generally nice and they do the training well with learning rates. However, there is a big problem. You need to have a small learning rates in order for the model to be able to find the minimum of the function to be able to optimize. Because if you have too big of a learning rate, it can jump over the minimum and it might not converge well to the best solution. However, low learning rates slows down the training because at each time you are just changing the weight a bit, and you to reach the optimal value, you should run more epochs, and each epoch is costly. So it would slow down the training. You may think, but training was fast, like 20 epochs was nothing. Yes, of course. But in many big neural networks that are running now, for example, I don't know, like when OpenAI wanted to train GPT, which is like a very, very big neural network, of course, they need to speed up the training and to find a lot of ways to do that. So there are different ways that you can do, not only to improve the training speed, but also to improve robustness of the model and to improve the accuracy. One of them is called batch normalization. Basically, for batch normalization, for each batch that you are training the model with, you find the mean and the standard deviation of that batch, and then you normalize the values based on that. This is just a simple trick that you can actually apply easily into PyTorch code. As you can see, before just passing to the next layer, you just n.batch norm1d. It's just simple batch norm, and you specify parameters. So it's just verify. This would help usually make the model more robust to the initialization, and you just have to add them basically, for example, after activation function or whatever you want. Maybe before. I think we can also put them before as check. But the thing is, for batch normalization, people do not suggest it's used for RNNs. And basically for RNNs mostly, and also for time series data, also in transformers, we use another type of normalization called a layer normalization. For layer normalization, we don't consider batches, but we consider each layer. And for all inputs of that layer, we normalize them together. Like, for example, we have a certain layer in our network, and we have some input data to that layer. Each of them have a value. We calculate the mean and the standard deviation of that value, and we normalize them. You see in practice tomorrow how it is used mainly in transformers. In the transformer architecture, this is the central piece that when you have multiple inputs to one layer, you normalize them. So basically, you can also see the formula. It's nothing very fancy. You just calculate the standard deviation. You also add an epsilon in the bottom of the fraction, so that if the variance is 0, it would not make any problem for us. The epsilon is just for avoiding division by 0, because all the values can be the same, then the variance is 0, right? And then you just subtract the mean from each data point, divide it by standard deviation plus that epsilon thing, and then it would output. Also in torch, it's pretty easy to do. It's like torch.n.layer norm, similar to the code that we just saw, and it's common in transformers that you will see tomorrow. It's just a very quick recap that we will all see it in practice, how layer norm is used in a real architecture tomorrow. Any questions? Fine. I think it's fine. So I think we finished today a bit faster than expected. I know I speak too fast, so sorry for that. But I hope it was fine. And I mean, the goal was to finish it earlier again, because you voted for 2 sessions. One idea was to 4 to 7 p.m. and we cutting some stuff, not for example doing coding, or 2 sessions of 4 to 6. So I think for tomorrow we'll also do the same. We'll start from 4 and we finish at 6. That's the general goal. So just as a tip, remember that room for tomorrow is not this room. It's seemingly BC229, but if it changes, it will be announced in Discord. So please follow the Discord. I think because this room is booked for, I think someone is doing a defense or something, I don't know. So we will, I think, meet each other at BC229, which is just the second floor here. Any questions? All right. Yes. Uh-huh. Okay. Uh-huh. Good point. So for ESS, I mean, actually, I don't know. Like for CNNs, I don't know when they applied in the CNN part, to be honest. I'm not an expert in CNN at all. Like, I mean, if you apply them in the feed-forward layer, it's fine over there. Because, but I mean, you are considering about the image part first. I don't even know if they do layer normalization there. I should check this. To be honest, I don't know about CNNs. Like, last time I did CNNs was like 10 years ago. I don't remember. I don't know a lot about CNNs. I should check. But yeah, write it in Discord so that I will check it out. But for time series data and all of this, it's pretty simple. So you can do it and it's fine. Because in the end, we are caring about integer values. Also for algorithms, it should work because they're relative to each other. So I don't think it's a big problem. But I should check. Yeah. Sure. Oh.